Hey everyone! So how do we know if two groups are different from one another? How do we know if one group mean is bigger than another group mean? How do we know if two groups actually have differences that are statistically significant from one another? We use t-tests, so let's review different hypothesis testing methods. We're going to go over the details of one-tailed hypotheses and two-tailed hypotheses, when it's appropriate to use each, and how to calculate each by hand. Let's review t-tests. T-tests help us statistically compare groups. To compare groups, we use two samples and we compare them using two values. And you might see different textbooks or statisticians use different words, but for the purposes of our course, we're going to call them t-calculated and t-critical. T-calculated is what you calculate by hand using a formula, and t-critical is what you're going to return as your t-score from a Bognar app. Once we obtain these values, we compare them and we make assumptions about the groups at the population level. So again, we have two samples from different groups and we're comparing those samples. We can probably tell the differences in the standard deviations and the means of these samples, but we want to use the information about the samples, the means, and the variance of those samples to make inferences about the population. So here are two practice problems. Can you determine which test is appropriate for each of these two problems? Let's look at example 1. A sociologist is interested in the average number of alcohols consumed by students and whether the average value varies by the type of undergraduate institution the student attends. A random sample of 250 students at community colleges showed that on average, students drink 24 ounces of alcohol with a sample standard deviation of 4 ounces. A random sample of 250 students at four-year universities showed that on average, students drank 32 ounces of alcohol with a sample standard deviation of 6 ounces. And the question is, does the average value of alcohol consumed vary by the type of undergraduate institution the student attends? So which test is the right test to use in this situation? We know our two institution types that we're comparing, community colleges and four-year universities. We haven't been asked whether students drink more or less at one institution compared with the other. So if we are just looking for any variance or difference without a direction, the appropriate test is a two-tailed test. And let's just make sure we can flag the important information from this problem. The community colleges, you have your N for group 1 here. You have your mean of group 1, X bar, and you have your standard deviation of group 1. And then you have your N of group 2, which is your four-year universities. You have the mean, X bar, and then you have your sample standard deviation, 6. Perfect, this is all you need to calculate your t-test. Let's look at example 2. A public defender is curious as to whether women receive higher speeding ticket fines than men in her district. She asks the police to send her a random sample of citations, which include, among other details, the gender and fine amount associated with that ticket. In this sample, there were 120 women, and their mean speeding ticket fine was $237, and the standard deviation was $59. Also, there were 135 men, and their mean speeding ticket fine was $287, and their standard deviation was $38. Compare t-critical and t-calculated. What conclusions can you draw from this t-test? Well, again, we want to think about whether we're being asked for any difference or any directionality between these two groups. The first sentence of this practice problem asks us whether women receive higher speeding ticket fines than men. That gives us directionality. That's saying, do women have greater speeding ticket fines than men? That directionality gives us the indication that we should use a one-tailed test. We're going to go through each type of test, and we're going to use a practice problem that we talked about before to show how to do these steps together. So let's review. What are two-tailed t-tests? We're saying that our alternative hypothesis means that our two means are not equal. They are statistically different at the population level. You have two groups of observation, and each observation is only in one group, so there is no overlap between groups. You hope to test differences with a quantitative continuous variable, usually an interval or ratio variable. You assume that your two groups are samples that are the result of random sampling. There are more assumptions that we're considering statistically, but those go beyond the scope of our course. The big question you want to answer is, are the means of two independent groups statistically different from one another? You could look at just the point estimates, which are the means of the samples, and say whether they're equal or not, but what about the variance or spread of each sample? Is there overlap when we look at the population level? Your first step is to identify and organize the details of the problem and calculate when and if necessary. Whenever you're completing problems like this, you want to organize all your details. You want to identify your two separate groups. And in these problems, in two-tailed t-test problems, we're only looking at the difference between groups. We don't care about directionality. So it doesn't matter which group you decide to put first. You want to identify the quantitative continuous variable you're testing and make sure you include your units, like a good social scientist. You organize your sample means, which are x bar 1, x bar 2 for each group, standard deviations for each group, S1 and S2. Sometimes you might be given the variance. If you're given the variance, remember that by definition, variance is S squared. So if you aren't given S, you can write down S squared. It actually saves you a mathematical step, so you can fill in these lines. However, in these practice problems, I've given you S, not the variance. Sample size of each group. You can have different sample sizes for each group. You'll see in some problems they're the same and some they're different. That's okay. And then you're going to calculate the degrees of freedom. For these kinds of problems, because degrees of freedom are calculated differently for many different kinds of statistical tests, for t-tests, degrees of freedom are calculated by adding your two sample sizes together and then subtracting 2. Finally, set the alpha level, and we're usually going to set it at 0.05 or 5%. That's our scientific standard for significance. Again, a few reminders. Your x bars, your sample means that you get for each group, are most likely not going to be equal. Neither will your s's, your sample standard deviations. That's okay. We're using these sample statistics to test whether the population means are equal using those samples. So here I've taken the information from the practice problem that you have, testing whether community college students and four-year college students drink different amounts of alcohol on average at the population level. So I've organized that information in this table. If you're doing these problems for homework or on a test, make sure to download the worksheet so that you can organize your information clearly, cleanly, and quickly. Our next step, step 2, is to set up our hypotheses. For independent samples, two-tailed t-tests, we always set up the following mathematical null statement or null hypothesis statement. A null hypothesis would be that the mean at the population level of group 1 equals the mean of group 2 at the population level. That means that there's no statistical significant difference between the means of these two groups. The translation into narrative form is that the null hypothesis states that in the population, the means of your quantitative continuous variable are equal across your two groups. You want to write your null hypothesis in a sentence using the variable name and group names from the problem. I'll show you that on the next slide. Now remember, for independent samples, two-tailed t-tests, we always set up the following mathematical alternative hypothesis statement. The alternative hypothesis is that the mean of group 1 at the population level does not equal the mean of group 2 at the population level. Mu1 could be greater than mu2, mu1 could be less than mu2. It doesn't matter. We're just proving that there is a difference between the two groups. So we can't say which one statistically has a higher or lower mean than the other. The alternative hypothesis translation states that in the population, the means of your quantitative continuous variable are unequal across your two groups. Unequal is the same thing as saying different. Again, you're going to want to write your alternative hypothesis in a sentence using the variable name and group names from the problem. I've done that using our practice problem. Let's take a quick peek. Our null hypothesis would be that there is no difference in the number of ounces of alcohol drunk on average by community college students and four-year college students. Our alternative hypothesis doesn't say who or what group will drink more on average. We're just going to say that there is a significant difference between the alcohol drunk between two groups. The alternative hypothesis is there is some difference in any direction in the number of ounces of alcohol drunk on average by community college students and four-year college students. Now I wonder, what's your perspective? What do you think? On average, do you think at the national level, four-year college students drink more per week on average than community college students, or vice versa? There's a lot of different social factors that could play into that problem. In this case, we're just looking to see if there's any difference. So here's step 3. When we're doing two-tailed t-tests, looking at differences, we have to calculate t-calculated and determine t-critical. So as you know, t-calculated is determined by plugging in all the information from step 1 into this calculation. The calculation may look a little daunting, but it's really easy to solve when you just plug in the information from step 1. In the numerator, you have x bar 1 minus x bar 2. So you can calculate that easily first. That's just your group 1 mean minus your group 2 mean. Then I like to solve from the inside outward. So first I plug in all of my information. S is your sample standard deviation, so you're going to put that from group 1 and group 2 here. You're going to square those values. If you're given the variance, you can just put the variance in these two numerators for each group, and you don't have to square it. By definition, the variance is your standard deviation squared. These are n, your group sizes for each of your two groups. So I'd first solve each of these fractions, add them together, and then that final sum, I would take the square root of it. Once you have that, just divide your numerator by your denominator, and you're good to go. You'll have your t-calculated value. Now you'll want to take the absolute value of t-calculated. Mathematically, that just means if it's positive, that's great. If it's a negative number, make it positive. Second, t-critical is determined by using the Bognar T app, and you have this link, but here it is again in short form. We're looking for a proportion in two tails combined. We're usually using an alpha level of 0.05, so you enter that into the red box. Make sure to enter your degrees of freedom in the DF box. And in that drop-down, make sure that you select this option. You're telling the app to distribute the probability into the two tails, equally on either side. The returned x value in the blue box on the left is your t-critical value. You can take the absolute value again, just to be sure, and write your t-critical here. Sometimes negative t-calculated values will happen, just like negative t-critical values. It's best to take the absolute value of both of these two values so you can make sure you're comparing difference and not directionality. I've done the math for you here, so you can see I've plugged in the information from our practice problem, our group 1 mean minus our group 2 mean. This is S from group 1, so I've multiplied it by itself. I'm dividing by the sample size. I'm doing the same thing here. This is S2 multiplied by itself, divided by N2. So I solve all that information. I do the multiplication and division to get to these two simple numbers. I add them together, and then I take the square root. I get this value. I want to take the absolute value of this fraction when I calculate it. So I've calculated that our t-calculated is 17.78. You might get a slightly different answer depending on if you did some rounding, but this is pretty good to go. Then I went to the Bognar app. I entered degrees of freedom as we've talked about. I selected the right option to get the probability to be distributed between the two tails, and I got a t-critical of 1.96 for an alpha level of 0.05. Next, we compare t-calculated and t-critical. What we are doing, in essence, is determining whether we can say that t-calculated is greater than what is necessary to determine the groups are different with statistical significance. Our mathematical question is Is the t calculated greater than the absolute value of your t critical? If yes, the null hypothesis, H null, can be rejected, and you accept the alternative. The alternative hypothesis is that the mu, the population mean of group 1, is not equal to the mu, the population mean of group 2. This means the population means mu1 and mu2 of the two groups are unequal at a p level of 0.05. If no, the alternative hypothesis, HA, should be rejected. You would accept the null. The null hypothesis states that at the population level, there is no difference between mu1 and mu2. Mathematically, there is no difference means that mu1 equals mu2. The population means mu1 and mu2 of these two groups are equal at a p is less than 0.05 significance level. Finally, we want to write our results in a reportable full sentence. Here's the formula that makes sure that you get all of the important information into your sentence every time. Fill in these highlighted pieces with the data from your question. You would put group 1 here and group 2. You would select whether they do or do not have equal, and you would insert your variable and units, comma, and then you would write t, you would enter your degrees of freedom here, equals, you would have your t calculated value here, comma, p is less than, and then you would put your alpha level from the problem. So here's an example that's not related to our practice problems. Women and men do have an equal number of years of education. T, and then a degrees of freedom, 59 equals, and here's a t calculated value, and then here's p, your alpha level. Important, we can't conclude that your groups cause or don't cause the changes in your variable. You may have heard the phrase, correlation does not cause causation. A t-test does not suggest causation either. It demonstrates whether there is a possible correlation, that there might be a relationship between belonging to a group and a difference in a variable outcome. In our practice problem, we could report the results from our test as follows. Community college students and four-year college students do not drink equal ounces of alcohol. T, the degrees of freedom, is 498, and our T value is 17.78, that's our T calculated, and our P level is less than 0.05. Again, we're not saying that going to community college or a four-year college or being one of those students causes the differences in ounces of alcohol drunk on average. We're just saying that there's a correlation. We're seeing a pattern that there is a difference, that they do not drink equal ounces of alcohol on average. Now let's review. What are one-tailed t-tests? We have the same assumptions for this test as we do for our two-tailed t-tests. However, we have a different question we want to answer. Are the means of two independent groups statistically different from one another in a specific direction? There are a few ways in which you could assess this directionality. Is group 1's mean greater than group 2's mean? Is group 1's mean greater than or equal to group 2's mean? Is group 1's mean smaller than group 2's mean? Is group 1's mean smaller than or equal to group 2's mean? In step 1, we're going to first determine our directionality. We're going to set up our directional hypotheses, including our greater than or less than signs. That helps make sure that we're on the right track for when we pull the information from our problem. So here's my tip for setting up directional hypotheses. You want to start with the alternative hypothesis, which is, in other words, what the researcher wants to demonstrate. The null hypothesis should be then the null hypothesis should be the opposite of the alternative hypothesis, and it should include all other possibilities. For the alternative hypothesis, fill in the following statement mathematically. Your alternative hypothesis is such that your population mean of group 1 has to be something compared to the population mean of group 2. It could be greater than or equal to, less than or equal to in this spot. You would put any of these signs into this space. Then you'll want to write your alternative hypothesis in a sentence using the variable name and group names from the problem. Then for the null hypothesis, fill in the following statement mathematically. This hypothesis needs to include every other possibility that the alternative doesn't include. So for example, if your alternative hypothesis was that mu1 is greater than mu2, then the null hypothesis has to be that mu1 is less than or equal to mu2. Here's another example. If your alternative hypothesis is that mu1 is less than or equal to mu2, then your null hypothesis should just be a greater than sign, not including an equal sign. So mu1 is greater than mu2. A good way to know that you're doing this right is that you're going to have one sign that doesn't include an equal sign in it and one sign that does in every hypothesis pairing. Write your null hypothesis in a full sentence and you're good to go. So here's our practice problem that is a one-tailed test problem. For our alternative hypothesis, we're going to say that we want to know whether women, group 1, have higher or greater than speeding ticket fines than men who are group 2. So in a sentence, our alternative hypothesis is that women have higher speeding ticket fines than men. And then our null hypothesis has to include every other possibility. So women have lower or equal speeding ticket fines compared to men. Next, we want to make sure we capture all of our information in step 2. We have determined which groups we're talking about, and your order of your groups does matter for these problems. And then you'll fill in the rest like we've talked about with the previous practice problem. I've filled out this using our practice problem about women, men, and speeding fines. So as you can see, I've got group 1 is women, group 2 is men. Our quantitative continuous variable we're testing is speeding ticket fines, measured in dollars. Here are sample means of our two groups, our sample standard deviations of the two groups. We weren't given the variance, and that's okay. Usually you're either going to be given this or this. Here are different sample sizes, and again, it's okay to have different sample sizes for our two groups. All we have to do to calculate our groups of freedom is add these two together and subtract 2. So this is our degrees of freedom. And we've set our alpha level to 0.05. We weren't given something else by the problem. If the problem doesn't suggest an alpha level, use 0.05. Step 3 is actually calculating the t calculated value again. Here, we use the same formula as before. We just don't take the absolute value no matter what comes back from the calculation. And then t-critical is calculated using the same Bognar T app. Here's a handy reminder of which to select to put your tails together for your test. So if your alternative hypothesis has the less than or equals to sign when comparing mu1 or mu2, you want to make sure that that matches in the drop down on the app. And if your alternative hypothesis has a greater than or equal to sign between mu1 and mu2, again, you want to match the directionality to select the right tail. So remember here, the positive or negative t-calculated or t-critical values are important for us completing this test, so do not take the absolute value of either of them. I've done the math for you on this practice problem. I'll let you walk through the specifics at home, but again, I've just plugged in the values and then methodically calculated inside out. What I mean by that is that I do the simple math, the addition and subtraction first, or the squaring. So I do the numerator, that's easy to solve. I make sure to do the squaring of our s values. Then I solve those fractions to something simpler, add them together and take the square root. And then I'm given our t-calculated value by calculating this, and I do not take the absolute value. I like that it's negative. That's important for our calculation. Then I figured out t-critical by using the Bognar T app, making sure that the directionality is aligned correctly, and then I've entered the correct degrees of freedom and our alpha value into the app, and I've returned the value of 1.65 as t-critical. Now, if your alternative hypothesis it has this less than sign between mu1 or mu2 or less than or equal to, that means you're determining whether the returned t-calculated variable is significantly small enough to be below than or less than t-critical. So is the t-calculated value less than or equal to the value of your t-critical? If yes, the null hypothesis can be rejected and you accept the alternative. The translation is that mu1 is less than or equal to mu2 at a p equals 0.05 significance level. If not, then the alternative hypothesis HA should be rejected and you accept the null instead. This means that you were trying to test to see if mu1 is greater than mu2. You were trying to test to see if mu1 was less than or equal to mu2, and instead the test is telling you that mu1 is greater than or equal to mu2. If your alternative hypothesis is that mu1 is greater than or equal to mu2, you're determining whether the returned t-calculated variable is significantly large enough to be above or greater than t-critical. So your mathematical question is the t-calculated variable greater than or equal to the value of your t-critical? In that case, if yes, the null hypothesis can be rejected and you accept the alternative. That means that yes, you were testing whether mu1 is greater than or equal to mu2 at a p is less than 0.05 significance level, and you found it to be true. If no, the alternative hypothesis, HA, should be rejected. Instead, you would accept the null. The translation is that mu1 is less than or equal to mu2 at a p equals 0.05 significance level. In our case, we were trying to figure out if women, which was group 1, had higher speeding tickets on average than men, which was group 2. That means our alternative hypothesis was set up in this direction, mu1 greater than mu2. However, our t-calculated value was not greater than or equal to the value of our t-critical. It was much less. So since the t-calculated was not greater than the value of our t-critical, we should reject the alternative hypothesis and we have to accept the null. That means that women's speeding tickets are less than men's speeding tickets at a significance level of 0.05. For step 5, all we have to do is write out our results in a reportable full sentence. In our case, for this practice problem, we saw that women do not have greater speeding ticket fines than men. And we insert our degrees of freedom here. So T of 253 equals negative 1.26. P is less than 0.05. Again, does that mean that your gender causes the differences in your speeding ticket fine level? No, we're not saying there's any causation between these two variables' relationships. We're just saying that instead they're related or correlated, or there may be a relationship between these two variables, gender and speeding ticket fines, but not that one causes the other. Here are my top 3 takeaways from this video. They're not comprehensive, but they're just to make sure we're all on the same page. Remember that two-tailed tests involve difference. Our two-group means significantly different in any way. One-tailed tests involve directionality. Is one group mean bigger than or equal to the other? 3, practice with word problems. It's really important that you know how to translate a word problem, which we'll encounter in social science all the time, into a mathematical problem that applies your mathematical knowledge into a real-world situation. Thanks, everybody.